Hello and welcome to this second set of 10 problems on arithmetic progression, numeric progression and harmonic progression. So as always, I will say that when I read the problem, you should pause the video and try to solve the problem yourself. If you cannot solve the problem, then you should look at the solution. So without further ado, let's get started. Problem 11 says that in an AP of two n terms, the middle pair of terms are p plus q and p minus q. Show that the sum of cubes of the terms in AP are 2np multiplied with p square plus 4n square minus 1 q square. So we let tr denote the nth term of AP. So our nth term would be p plus q and n plus 1th term would be p minus q. So subtracting these, we get common difference d as minus 2q. Also, we know that the sum of first and last term, second and penultimate term is equal to sum of middle terms, which will be equal to 2p. Now we let s to be the sum of cubes in terms of AP. So s would be t1 cube plus t2n cube plus t2 cube plus t2n minus 1 cube and so on. Now if you look at the first of these terms, that is t1 cube plus t2n cube, we can rewrite that as t1 plus t2n whole cube minus 3t1 t2n multiplied with t1 plus t2n. We substitute 2p for t1 plus t2n, so we get 8p cube here minus 6p t1 t2n. Now t1 t2n can be written as t1 plus t2n whole square minus t1 minus t2n whole square. This will give us 4 t1 t2n, so we divide here by 4. Now we rewrite this over here again. We know that t1 plus t2n is 2p, so this becomes 4p square over here, and we know that t2n is equal to t1 plus 2n minus 1d, that is t1 minus t2n would be 2n minus 1d and d is minus 2q. So we rewrite here, so it becomes 2n minus 1 whole square dot 4q square. So the entire value of this expression is 2p cube plus 6pq square multiplied with 2n minus 1 whole square. Now continuing this, we will find t2 cube plus t2n minus 1 cube is equal to 2p cube plus 6pq square, like this one, and this term will vary, 2n minus 3 whole square. For the next pair of terms, it would become 2n minus 5 whole square, and for the last pair, that is the sum of middle terms, it would be 1 square. So we add all this, we get 2np cube plus 6pq square, and in the bracket we have 1 square plus 3 square plus 5 square up to n terms. The sum of this would be, the sum of total would be 2np into p square plus 4n square minus 1 multiplied with q square. Problem 12 says that find the sum Sn of the cubes of the first n terms of an AP and show that the sum of first n terms of the AP is a factor of Sn. So we let S to be the sum of n terms of the AP, and the terms are A plus D, A plus 2D and so on. So S would be n by 2 into 2A plus n minus 1 into D. Sn would be A cube plus A plus D whole cube plus A plus 2D whole cube up to A plus n minus 1 into D whole cube. So this, we take out the terms of a cube from this and so on. So we get na cube. The 3a square d term will start coming from here. We take that out, and the bracket would be the multiples of d, that is 1 plus 2 plus 3 and so on. Then we take out 3ad square. In the bracket would be square of 1, 2 up to n minus 1, and for d cube it would be 1 cube plus 2 cube up to n minus 1 whole cube. So we rewrite all this by this. You can look at the solution, and we take out 2a plus n minus 1 into d. So this n by 2 into 2a plus n minus 1 into d is s, and in the bracket we have a square plus n minus 1 into ad plus n. Okay, I messed this up. This is wrong. This bracket should be here, n into n minus 1 by 2d square. I'll correct this in the upload. Problem 13 says that show that any positive integral power greater than 1 of a positive integer m is the sum of m consecutive odd positive integers. Find the first odd integer for m to the power r, where r is greater than 1. So for us, r is a positive integer, that is r greater than 1. So we let that m to the power r is equal to 2k plus 1 plus 2k plus 3 up to 2k plus 2m minus 1, that is m consecutive integers over here. So we have m to the power r is equal to m by 2 multiplied with 4k plus 2 plus m minus 1 into r. So we cancel out r, left hand side becomes m to the power r minus 1 and right hand side becomes 2k plus m. So k becomes m to the power r minus 1 minus m by 2. So as long as r is greater than 1, m to the power r minus 1 and m will be odd or both will be even. So m to the power r minus 1 minus m would be an even number. Thus, since this would be an even number, k will exist, because when you divide an even by 2, you will have an integer. So the integer would be 2k plus 1 here. The first integer is 2k plus 1, which is equal to m to the power r minus 1 minus m plus 1 from here. Problem 14 says that if a be the sum of n terms and b square the sum of square of n terms of an AP, find the first term and common difference of the AP. So we let x to be the first term and d to be the common difference. Then our series is x plus d plus x plus 2d and up to x plus n minus 1d is equal to a. So this implies, by substituting the formula, we have nx plus d into n into n minus 1 by 2 is equal to a. Now we square this to get nx square plus d square multiplied with n minus 1 whole square n by 4 plus n into n minus 1 xd is equal to a square by n. The sum of squares of the terms is x square plus x plus d whole square plus x plus 2d whole square plus up to x plus n minus 1d whole square, which is equal to b square. We solve this equation to arrive at nx square plus d square multiplied with n minus 1 into n into 2n minus 1 into by 6 plus 2xd into n minus 1 by 2 is equal to b square. So we subtract this equation and this equation. So we get, upon subtraction, we get d square multiplied with n into n minus 1 into n plus 1 by 12 is equal to nb square minus a square by n. So from this we get d as plus minus 2 square root of 3 nb square minus a square divided by n square root of n square minus 1. So from this we can find out our x by substituting in one of the equations, or by substituting over here you can find x. Problem 15 says that if a1, a2 up to an are in AP whose common difference is d, then find the sum of the series sin d into cosec a1 into cosec a2 plus cosec a3 cosec a2 cosec a3 plus up to cosec an minus 1 cosec an. So this is similar problem like one we have solved earlier, where the term in bracket was sec. So you expand sin a2 minus a1 for this, and in the denominator you have sin a1 a2, and sin a2 minus a1 would be sin a2 cos a1 minus sin a1 cos a2. So when you divide, you get cot a1 minus cot a2. Similarly, for second term, you would get cot a2 minus cot a3. For sin d, for the second term, for sin d, you substitute sin a3 minus a2. So you will get cot a2 minus cot a3. We proceed this up to tn minus 1th term, which will be cot an minus 1 minus cot an. So we add all this. We'll see that cot a2 here gets cancelled with this. Cot a3 will get cancelled with the t3 and so on. So in the end, what you will have is cot a1 minus cot an. Cot an. So the entire result would be cot a1 minus cot an. Problem 16 says that if a1, a2 up to an are in AP where ai greater than 0 for all I, show that 1 by square root of a1 plus square root of a2 plus 1 by square root of a2 plus square root of a3 plus up to 1 by square root of n minus 1 plus square root of n is equal to n minus 1 divided by square root of a1 plus square root of an. So our first term is 1 by square root of a1 plus square root of a2. we multiply numerator and denominator with square root of a2 minus square root of a1. So with that, the denominator becomes a2 minus a1, which is d. So the term is 1 by d multiplied with square root of a2 minus square root of a1. You proceed similarly for second, third, and up to n minus 1 terms. T2 will be 1 by d multiplied with square root of a3 minus square root of a2. And Tn minus 1 would be 1 by d square root of an minus square root of an minus 1. There should be a square root over here. So now we add all this. We will have square root of an and square root of a1. a2, a3 and up to an will get cancelled. So we have s is equal to 1 by d square root of an minus square root of a1. So we multiply this with square root of a1 plus square root of an. We get it as 1 by d an minus a1. This should be a1 by square root of a1 plus square root of an. Now n minus a1 would be n minus 1 into d. D gets cancelled and the result is what we need. Problem 17 says that if a1, a2 up to an are in AP whose common difference is d, show that sigma, where limit of n varies from 2 to n, tan inverse d by 1 plus an minus 1, an is equal to tan inverse n minus a1, this should be a1 by 1 plus an a1. So T1 is tan inverse d by 1 plus a1 a2. So we can rewrite this as a2 minus a1, d is a2 minus a1 by 1 plus a1 a2. Now from the formula of inverse trigonometric functions, this can be written as tan inverse a2 minus tan inverse a1. Similarly, T2 can be written as tan inverse a3 minus tan inverse a2. We proceed this up to Tn minus 1th term. So that would be tan inverse an minus tan inverse, this should be power, not tan square minus 1. This is tan inverse a n minus 1. Now if you see this, tan inverse a2 will get cancelled, tan inverse 3 will get cancelled, and you proceed in this way, tan inverse n minus 1 will get cancelled. So the final result should be tan inverse an minus tan inverse a1, that is this term. This can be written as tan inverse an minus a1 by 1 plus a1 an. Problem 18 says that if a1, a2 up to an are the first n items of an AP with first term a and common difference d such that ad greater than 0, let Sn is equal to 1 by a1 a2 plus 1 by a2 a3 plus, this should be plus, up to 1 by an minus 1 n. Prove that the product a1 an Sn does not depend on a or d. So like earlier, we solve this, and Sn, which we have arrived earlier also, is equal to n minus 1 by a1 an. So if you see this, a1 n Sn will become n minus 1, which is independent of a and d. Problem 19 says that if a1, a2 up to an and n plus 1 and so on be in AP whose common difference is d, and S1 is equal to a1 up to n plus a2 up to n, S2 is equal to n plus 1 plus so on up to a to n, S3 is equal to a to n plus up to so on up to a3n. That is, S1 is sum of first n terms, S2 is sum of next n terms, and S3 is sum of final n terms. So that S1, S2, S3 are in AP whose common difference is n square d. So S2 minus S1 we evaluate. So the first term of S2 would be 2an plus 1, because an plus 1 would be the first term. So we multiply that with 2 to get the sum, plus n minus 1 into d, and n minus 1 d will come here as minus, and the first term of second series is 2a1, n is number of terms. Now when you subtract this, n minus 1 d will get cancelled, and 2an plus 1 can be written as 2 into a1 plus nd. So 2a1 will get cancelled, and what you will have is n square d. Similarly, if you solve s3 minus f2 or s4 minus s3, all those will be n square into d, because the only difference will come from this term and this term, and these two terms are n terms apart. So since they are n terms apart, the difference will always be 2n square d and 2nd, and 2nd when multiplied with n by 2, it will give n square d. Problem 20 says that if A, B, C are three terms of an AP such that A is not equal to B, show that B minus C by A minus B is a rational number. So we let X to be the first term and Y to be the common difference. We also let A, B, C to be the PH, QH and Rth term of the AP. So A is equal to x plus p minus 1 into y, B is equal to x plus q minus 1 into y, C is equal to x minus r into 1y. So what we have to prove is that b minus c by a minus b, that is q minus r by p minus q, is a rational number, which is true because p, q, r are all integers. So q minus r by p minus q will be a rational number. With this, we come to the end of second set of 10 problems. In my next video, we will solve 10 more problems. And if you have found this video useful, please subscribe to the channel and like the video, because that motivates me to make more such videos. Also, if you have a question or you want to say something about these videos, please comment, and I definitely will answer to the comment. So enjoy solving the problems. I'll see you in the next video.